Now, okay, so we're now broadcasting. I'm not sure if this means anybody's in the talk yet. I guess we'll see. Okay, we've got a few participants. Great. Okay, good morning and welcome everybody to our second sponsored talk from IBM Research. Today, I'm delighted to have Dr. Zhaokui Xu with us from IBM Research, who's going to be talking today about unleashing cyber reasoning, DARPA transparent computing, a threat hunting perspective. Zhaokui is a researcher at IBM TJ Watson Research Center. He works on theoretical and practical aspects of system security. He approaches security as an interdisciplinary problem and connects it with related fields such as formal methods, machine learning, programming languages, and human interaction. He's been focusing on cyber reasoning after joining IBM, and we'll talk about some interesting experiences with the transparent computing program today. We'll give people about 30 seconds more to join before we start the video. So Zhaokui, if you want to say a few words before we get started.
Thank you, Kevin, and thank you for providing me the opportunity to have the talk. And it's a great pleasure. And then also, if anyone has questions or want to discuss more, so we have a few minutes after that, and I'll be happy to answer questions and have more discussions.
Yeah, we'll have the we have the live Q&A after the talk. Please feel free to put questions in the chat window, and Zhaokui will be around afterwards as well. So please, even after the session, you can continue to put questions in the chat or to message him directly. Okay, so let's get started with the talk.
Good morning, good afternoon, and good evening. Thanks for joining the talk. I'm Zhaokui, and I'm leading the Cyber Reasoning Initiative at IBM Research. In the past few years, we teamed up with Stony Brook University, University of Illinois at Chicago, and Northwestern University to research and develop new threat detection methodologies and systems in the DARPA Transparent Computing Program, or TC. We finished strong last year. Today, I will share with you some thoughts and insights we get about threats, about detection, most importantly, how we achieved effective threat discovery. It starts with a series of challenges. What can existing approaches detect? What advanced threats can attackers realize? And what is possible from defenders' perspective? When the red team in the program talk about their capabilities, and when we find the attack they implement, one thing is clear. They really want to go stealthy. They develop their own malware and in-memory attacks to nullify existing antivirus. They combine straightforward intrusions with insider threats and stolen passwords. They conduct benign and common activities, but with malicious intent to hide large portions of their attack campaigns. They understand the lack of precise training in real-world defenses, and they attack services without proper behavior models. Lastly, they are very smart and open-minded and usually jump out of the threat models we prepared before each adversary engagement. So what is an adversary engagement? DARPA designs a program with several players. The monitoring teams develop novel approaches to provide blue teams maximum visibility of systems in a controlled small enterprise network. The blue and red teams develop their strategies and approaches separately. Every few months, DARPA will create an adversary engagement that every team comes in and then things are happening in real time. The monitor data is streamed to blue teams while the red team starts to implement their attack campaigns. We, as a blue team, provide online threat detection and policy enforcement, and reports back to the red team. During the 4 years of the program, we developed a series of new technology and achieved effective detection and a leadership position in multiple adversary engagements. However, this does not mean we detect every campaign, every step. Detecting real attacks, stealthy real attacks, with no knowledge about them is hard. On the right is our detection results against some small attack campaigns named after their key steps or tools. Some are on a single device, some are cross devices, some attacks succeed, some fail, some are well monitored, some we cannot see. Some fall into our predefined threat models, some are out. To give you a concrete idea of the detection, here is an attack that Red Team implements against an Android device. Our real-time detectors with pre-coded knowledge and anomaly detection mechanisms report suspicious activities with thousands of alerts per day. We combine the alerts from multiple detectors, pick up highly suspicious ones, and perform threat hunting to discover attack stories behind them or eliminate false positives. For instance, this attack around Toybox is beyond the threat models or knowledge we encode into automatic detectors. Yet, one detector provides us valuable hunting leads to discover the main body of the attack. When we think about detection, it is indeed to find instances of threats according to our definition or knowledge of threats. Traditionally, on the left, we study threat models, program our knowledge into detectors, and deploy them to search for attack instances. This flow does not always work because we don't always know the threats well, especially new threat models or customized APT campaigns. The red teams in TC are open-minded and they like to jump out of the common threat models we prepared. As a countermeasure, we also jump out of the box, creating and evaluating new threat models and threat hypotheses during adversary engagements on the right. We call it dynamic cyber reasoning. One example, in an early engagement, I discovered the red team using VI to copy the password file, moving it several times, and finally transmitting out via Nginx. Although data exfiltration is something we prepare to detect, we need to understand what and how the red team is gonna to leak. This hunt provides us initial information to refine our data leak detectors. Second, when I discovered an Android process reading hundreds of pictures and writing corresponding files with special suffix, I realized it is a ransomware on a mobile device. This is an eye-opener to us, as we never thought about threats like this. Last one, after I confirmed some malware on a Linux box, I used the names as fresh indicator of compromise, or IOCs, for searching on other devices. Then I discovered some other attacks on a Windows machine. In summary, we found the traditional detection flow insufficient, so we created a dynamic cyber reasoning flow on the right to act. The key difference is where the knowledge is created and encoded into the detection procedure. Before seeing the real data from the target or after it. The biggest challenge of cyber reasoning is its efficiency. it takes weeks to months to develop security software. But here we only have minutes to hours to create new detection procedures for new threat hypotheses. Of course, we also need immediate execution of the procedures to provide us live feedback to revise and extend threat hypotheses. We study existing threat hunting practices and understand the pain points of threat hunters with incompatible data interfaces and non-standard methods to encode knowledge. So we take advantage of the graph data we get from the monitoring teams and recast threat discovery into a graph computation problem. Once we put all computing activities in a labeled temporal graph or computation graph, threat discovery becomes a problem to find a subgraph that belongs to the attack. To ease security analysts from cumbersome knowledge encoding, we let them write or draw graph patterns, and only graph patterns, to do all type of reasoning and hunting. A graph pattern can be as large as an entire APT campaign. It can be as small as just one event. It can be composed from smaller graph patterns. It can be shared, reused, and executed to return matched subgraph instances. We make the new cyber reasoning paradigm real with the full implementation of a domain-specific language, talk calculus. We publish its syntax. We build its runtime from scratch, including a distributed graph database for achieving good performance with big data in TC. We develop constraint solving algorithms to decode graph patterns into low-level database queries. We implement building graph traversal algorithms to ease the testing of connectivity between graph components. We build 3 user interfaces to handle automatic batch execution, interactive hunting, and computation graph visualization. We use the talk calculus platform in the TC program for scheduled TTP detection, interactive threat hunting, and real-time policy reasoning with data provenance rules. The idea of graph computation for cyber reasoning is platform agnostic, and we have discovered threats on all operating systems in the monitored small enterprise network. At the end of the talk, I'd like to quickly go over our second strategy that boosts our advantage in adversary engagements. The concept here is simple: more detection angles, less space to hide. For example, we can detect a malware by its binary signature, by its behavior, by its additional activities it introduces besides normal uses. The uncovered detection corner space, where attackers can hide, is much smaller across multiple detection mechanisms than a single one. In the TC program, our team brings up a comprehensive portfolio for threat detection, which has been proved an effective design against stealthy APT campaigns. More information about our approaches can be found in our blogs and papers. IBM is the largest enterprise security vendor in the US, and we have a lot of research and development going on in cyber reasoning. Feel free to contact me for more discussion and opportunities. Thank you.
Okay, thank you, Xiaokui, for a really great talk, a wonderful retrospective of the work that you've done in the program. And attendees, please, we have time for 1 or 2 questions. If you have any questions, please put them in the chat box. I'll start us off with a question. It was really interesting work. It seems that the way that you're able to take information from various sources and the graph deployments that you've got is impressive. What do you think are the biggest challenges with regards to both the incoming data collection and more generally widespread deployment of your reasoning architecture? What do you need to have deployed on your collection apparatuses to make this a usable in the general case for an enterprise, for example?
Thanks, Kevin. That's a very, very good question. And actually, we are taking a look at the gap between what the program provides and what the industry has now. And one big gap we still see is from data collection perspective, that there are very few vendors in the real world that can provide information as detailed as these in the TC program. And for example, from IBM Research, we are starting to build similar capabilities to provide the detection kind of teams and people the visibility into the system. And we started something called sysflow. That there are also other competitors in the industry and start to provide similar capabilities. And I think that will be the first step when we want to go further and adopt the methodology and things for better detection in the future in the real world.
Great. Yeah, I would love to see this deployed. There's so many interesting problems with regards to trustworthy provenance collection and the reasoning over the data that's collected there. That is a really rich area. We're at 11:31, so I know that many people need to get to other panels and issues. Please, if you have any other questions, if you have any last comments before we end, please feel free to put them in the chat. Otherwise, Jacques will be around and we'll be able to answer questions both through the public chat interface, and feel free to message him directly. You can do a face-to-face meeting, and I'm sure he'd be happy to chat. So thank you again, Jacques, for a really great talk and for IBM's sponsorship. And thanks to everybody for attending this session.
Thank you, Kevin, and thank you, everyone.